Hello and welcome back to Statistical Reasoning. We're moving on in Chapter 7. We're going to move into the concept of estimating a population mean using a confidence interval. Before we had done a population proportion. So symbols are very similar. The only difference is now we're using x bar instead of p hat and we're using mu instead of p. So some of the symbols, to be more specific, mu will be the population mean, n will be the number of the sample values, x bar is the sample mean, we're still going to use e for margin of error, and sample standard deviation is still s as it has been previously. Requirements that need to happen: if we do not know the population mean, we make sure we have a simple random sample, which is actually true for all things that we do in statistics. And then the other thing we need to do is that make sure we're either normally distributed or your sample size has to be greater than 30. It is critical that we realize it's an or, not an and. They both don't have to occur. To find our margin of error, we have a formula just like we did in the proportions. Our formula is E still for margin of error. This time, because we do not know the standard deviation for the population, we're going to use a t-score instead of a z-score. We're going to take that, we're going to multiply it by the standard deviation divided by the square root of n. And when we go to look up our critical value, it's important that we know we use the degrees of freedom of n minus 1. We're still going to do our confidence intervals, and 95% will still be the one that we use the most often. When we're looking at this, it talks about how the alpha over 2 is still the area in the right tail. But one thing you'll notice when we look at this table, it looks a little bit different, and it includes both one-tailed and two-tailed areas. If we need to round our answer, we need to make sure that we do it in the proper way. So if we have the original data set, we're going to move one more decimal place than what's in the original data set. If we don't know it, then we're going to go with the same amount of decimals that are in the actual summary statistics that were given. When we have to, if we actually have to find our t-score, we do that by doing t equals, and we have done this before, x bar minus mu over s divided by square root of n. Same formula that we've used before. We can use the table. We can also use some other information, technology, to help us find our critical value. I will be showing you how to use the table to do that. But before I do that, let's actually look at the visual of what's happening with the t-distribution. So the green one is the standard normal distribution. So that's our z-scores. If we switch and not know the standard deviation for the population, now it's a t. What you'll notice as you look at this, the red one is a t-distribution with a little bit larger sample size than the blue one. The larger the sample size, the closer you are to the z-score, which is the normal distribution standard. The farther or the smaller your sample size is, the more it differs. The middle here gets smushed down, or there's less data here in the middle. And what happens is as we make this smaller, the tails get pushed up. And so the data that's normally in the center here gets pushed out to the tails, and so they have to come up in order to accommodate that. So the smaller the sample size, the less data that's in the middle and the more data that's in the tails. This is just a recap of the things we've been talking about, but having it all in one spot. Okay, when we're doing our confidence interval, it's very similar to what we did with the p or the proportion. This looks a lot the same, where symbols are just different. Instead of using p hat, we're using x bar. Instead of using p, we're using mu. This is representing the population. We can write it out in this form, where we have a data number and then is less than our middle, less than our other data number, so our lower limit, our upper limit, or we can write it where we do a plus or minus situation. So let's look at how to find our actual critical value. We're going to go ahead and work with a 95% and a sample size of n equals 15. Excuse me. So we need to make sure we know what our alpha level is. So if we have a 95% confidence level, we're going to go 1 minus 0.95. That gives us a 0.05 significance level. And right now, we're just thinking about that we're taking this 0.05 and we're splitting it amongst the two different tails. So I have a little bit of it over here, and I have a little bit of it over here. So that 0.05 is being split between both tails. So now when I go look at my table, so here's what the table looks like. It's table A3. It's either in the fold out of your book, or it is in the back in the appendix. You have your degrees of freedom on the left-hand side over here. Notice on the top you have either an area in a single tail or an area in two tails. So if I go back to the picture previously, I'm working with area in two tails. And one thing I need to write down here before I go back is our degrees of freedom. Degrees of freedom is n minus 1. Our n in this case is 15. So we're going to go 15 minus 1. So we're going to use a degree of freedom of 14 to help us find our critical value, and an alpha of 0.05 in two tails. So here I have area in two tails. Here's my 0.05. So this is the column I'll be using. I'm going to come over here and I'm using a degrees of freedom. Actually, I'm going to use the highlighter. I have a degrees of freedom of 14. So I'm coming across here with the degree of freedom of 14. Here's my area in the two tails. So I'm coming down. They cross at 2.145. So the 2.145 is my actual critical value that I'm going to need to use in this scenario. So I would write that as T alpha over 2 is 2.145. Okay, so that's the first part. Now as we move forward, we need to be able to work with that information. So we have our point estimate depending on how it's given to us. If they actually give us the confidence interval to find the mean, we're going to take the upper limit add the lower limit, and then divide by 2. To find our margin of error, we're going to take the upper limit minus the lower limit and divide by 2. Same thing, the only difference is we're talking about a mean versus talking about a proportion as in the last section. So we also needed to be able to determine the sample size, so we'll go ahead and work on that. Same symbols as before. Notice this is a Z. If it's a Z, that means we know the standard deviation for the population. If it's a T, we do not. So the formula that we're going to use, N equals Z alpha over 2 times the standard deviation divided by the margin of error, and we are going to square that. If these, just like before, if you come up with a number that is a decimal, you always want to make sure you round it, and you always round up because you want to make sure you have enough data to make sure it works. So here we have, if for some reason you do not know the standard deviation and you can't use it, you use what's called the range rule of thumb. Excuse me. So you find the range of the data and you divide it by 4. Now this is just going to give you a best estimate. I'm not going to be able to know that it's exact. And so if you do have the standard deviation, definitely use it. This is only if you do not have it. Okay, so let's see what we can do to actually do a problem. So we assume that we want to estimate the mean IQ score for a population of statistics students. How many statistics students must be randomly selected for an IQ test if we want 95% confidence that the sample mean is within 3 IQ points of the population? So let's think about what we know. We know we're doing a 95% confidence, we are 3 IQ points within, so this is our margin of error, so this is our E. We also know that, okay, so let's see what we do have here. So let's start with the confidence. We know we have a confidence of 95%. So let's think about what it is. We have our our z-score, critical value. For 95%, that's actually one that we worked with last time, and so we're going to use 1.96. Because our alpha level is 0.05, right? 1 minus 0.95 is 0.05. We're going to have to be within 3 IQ points, so our margin of error is 3. Now as I'm looking at this, here's the formula. As I'm looking at this formula, I have the z value, I have the e, so the issue here is I need my standard deviation. And so I have to think about, what do I know about my standard deviation? One thing I just realized that is missing is that it doesn't give us the standard deviation, and so that actually needed to be given. So we're going to go ahead and use a standard deviation of 15. Let me get back on the right slide. So we're going to do a standard deviation of 15. We want to make sure in the problems that we're doing, and maybe I'll do another one here real quick, that you have that data given, and for some reason it was left off on our slides. So we're going to go ahead now and plug that into our formula. So n equals our z-score, so 1.96, times our standard deviation divided by our margin of error, and then I'm going to square that. That gives me about 96.04. Now, no matter how small this is, we always round up, so we would want to make sure we do 97 subjects in whatever this study is about, and in this case it was stat students. Okay? If we do somehow know that, we want to make sure that we use it. Now this one, we haven't done an example of a confidence interval yet, so let's go ahead and do that next. We have all the data, so we want to go ahead and figure this out. We have 15 births, we have a mean of 30.9. We want to do a 95% confidence interval estimating those, assuming that we know that the standard deviation is 2.9. So the first thing we should always do is check to make sure that we have our requirements met. So is this a simple random sample? We didn't take the data, so we're not sure, so we're going to go with assuming that we are. The sample size is n equals 15, which is actually not a large enough data set. And so what we should look into is this actually normal? And what we should do is actually put it into our calculator or put it into StatDisk and see if it is normal. By looking at the dot plot. I will put a video on to show you how to do that separately. Going with this, we're going to go ahead and do the process of showing whether it is or not. So let's do the confidence interval. We have a 95% confidence interval. We already know that in this case we're going to use a critical value of 1.96. It tells us that we have a known standard deviation of 2.9 hectograms. We have a sample size of 15. So we have to find our margin of error. Our margin of error is 1.96 times the 2.9 divided by the square root of 15. That gives us a margin of error of 1.46 or 1.47 approximately. So now to find our confidence interval, remember we take our mean, which we know to be 30.9, we subtract the 1.47 for the lower limit and we add it for the upper limit. So I'm going to switch colors. So I'm going to go 30.9 minus 1.47 and 30.9 plus 1.47. Now these are rounded values. So this one is going to be approximately 29.4. And this one's going to be approximately 32.4. Now we actually had our data set, they were whole numbers, so notice I went one decimal place after the whole number. And so it would look like 29.4 hectograms is less than the mean, which is less than 32.4 hectograms. So I am 95% confident that the true population mean of mean weight births for girls would fall between 29.4 hectograms and 32.4 hectograms. The big thing now is just to remember when you use what. If you know the standard deviation for the population, then you're going to do a Z distribution, and if you don't, then you're going to do a T distribution. In both cases, you want things either to be normally distributed or you want a sample size that is greater than 30. Okay, I'm going to do another example showing you how to do the determining whether it is normal or not, and I will make sure that you have instructions for your calculators. Have a good day.